Hi, it's ChemGal, and in this video we're going to talk about Sn1 and Sn2 reactions. First, let's examine the two mechanisms side by side so we can understand them better. On the left we have Sn1 and on the right we have Sn2. And if you notice, in each case the bromine is leaving and being substituted by this OCH3 group. And on the right the bromine is leaving and being substituted by this cyanide group. And that explains why it's called Sn. Sn stands for substitution. And so there's two different kinds of substitution. There's substitution 1 and substitution 2. And I'm going to go ahead and explain why in a little bit. But for now, let's discuss the mechanism. So in the first step for Sn1, the bromine is going to leave. And this is so common that we call bromine the leaving group. And sometimes we'll abbreviate it as Lg for short. And now this carbon here is missing a bond. Initially it had 4, but now it has 3. And so it becomes a carbocation. So we can make note that Sn1 goes through a carbocation intermediate. And so here is where our HOCH3 group jumps in. And so we know that carbocations are positively charged. So are they going to act as a nucleophile or an electrophile? Positively charged things like to act as electrophiles. So that's going to make our methanol a good nucleophile. Specifically, this oxygen here is the nucleophilic portion on the methanol. And remember that the arrow always goes from nucleophile to electrophile. So the lone pair on the oxygen is going to be used to form a new bond with that carbocation carbon. And so now we have oxygen attached with its hydrogen and its CH3 group. Now this carbon has 4 bonds again, so it's happy and it's going to be neutral. Remember that when carbon has 4 bonds, it is a neutral carbon atom. And what happened to this oxygen? Well, initially it had 2 lone pairs, but it used one of its lone pairs to make that new bond. So because it used this lone pair to make that new bond, it's only going to have that one lone pair left. So if we wanted to calculate the formal charge on this oxygen atom, formal charge is going to be equal to valence electrons minus surrounding electrons. And oxygen has 6 valence electrons, but surrounding it right now is 1, 2, 3, 4, 5. Remember, it's 1 from each bond and 2 from that lone pair. And 6 minus 5 makes for a total charge of positive 1. So here this oxygen is positively charged. Remember that we still got to get to our product. And so this is the last step of the mechanism. And we call this step the deprotonation step. What does proton sound like to you? You might have heard that in organic chemistry, proton is the same thing as hydrogen. And so it's used interchangeably. So if we're deprotonating something, we are taking a hydrogen away from it. So we can imagine that we're going to take this hydrogen away from the oxygen atom. And to do this, we can use the Br- molecule that actually hopped off in this step of the reaction. And so here we have methylene drawn its 3 lone pairs. And when it left, it gained a new lone pair in the form of this broken bond. And so now the bromine is going to have 4 lone pairs, and that makes it bromide, which is negatively charged. So if we want to reassess who will be our nucleophile and who will be our electrophile, the bromine is a very good nucleophile because it's negatively charged. Remember, nucleophile, negative charge. And therefore, our electrophile is going to be this structure over here because it is positively charged. And what's going to happen is the bromine is going to take this hydrogen away from the oxygen atom and throw those electrons onto the oxygen. And that's what's going to give rise to this product over here. Notice how this oxygen is not charged anymore. It is now neutral. And that's because it gained a new lone pair from the breakage of this bond. And so now it has 1, 2 lone pairs. And if we real quickly wanted to calculate the formal charge to verify that, it's going to be equal to valence electrons minus surrounding electrons. Oxygen has 6 valence electrons, and surrounding it right now is 1 from each bond. Remember, it's bonded to that methyl group and to this carbon, and 2 from each lone pair. So that makes for a total of 6 surrounding electrons and a neutral charge of 0. So this oxygen is not charged anymore, and it's now neutral. Now let's go ahead and do the mechanism for the SN2 reaction on the right. And the good news is that this mechanism is only one step. And so what's going to happen here is the cyanide is actually going to attack this carbon and kick off the bromine atom. And when it does so simultaneously, so that the bromide is going to leave and form as a byproduct, and our main product is going to be that cyanide substituting the position of the bromine to give us this product. And so that's it for that mechanism. So I just want to bring your attention back to SN1 for a minute. And here we have something called a fast step and a slow step. And so the slow step is going to be the bromine leaving. So this step right here is the slow step. And that happens when the leaving group leaves. Now we also have a fast step, and that's going to be the second part of the reaction where the nucleophile attacks. Why do you think this step occurs faster than the first step? Well, if we think about it, in the first step, all that had to happen was bromine had to leave. However, everything was neutral here, right? In the beginning, all was neutral, and we had to wait for something to happen. And that was very slow, it took very long. But in the second part of the reaction, we had this carbocation. And carbocations are very reactive because they're positively charged. And the carbon only has 3 bonds, so it's missing a bond, and that makes it very unstable and very reactive. So carbocations are very reactive, and so they react very quickly. That's why this is a fast step. Now, if we want to think about the reaction rate for this problem over here, who do you think we have to take into account? The fast step or the slow step? Who's going to tell us how long the reaction is going to take? And the answer is the slow step, because the slow step will determine how long the reaction is going to take, because the fast step needs less time to occur. If we wanted to draw the reaction rate for this mechanism, it would be equal to K, which is the rate constant, the concentration of our substrate, which I'm going to write as sub. So the rate here depends on one thing. And so that's why this is called an Sn1 reaction. The 1 indicates that this is going to be a unimolecular reaction, meaning that the rate depends on one step of the reaction, and that is the slow step. In contrast, SN2 stands for bimolecular. And that means that the rate of the reaction is going to be equal to K, the rate constant, times the substrate and times the nucleophile. For our SN2 reaction, the rate is going to depend not only on how fast our leaving group leaves, but also how fast our nucleophile attacks. And that makes sense because this is all happening in one step of the reaction. So it makes sense that the reaction rate is going to depend on both of these. And so because it depends on 2 things, we say that this is bimolecular, whereas SN1 depends on one thing, and so we say that it's unimolecular. Now that we know all of this, we can make a diagram to map out the differences between the two, because it goes a little bit deeper than this. So now we've already established that SN1 is unimolecular, and that's because the reaction rate depends on one thing. It's going to be equal to the K constant times the substrate, and that's why we call it SN1. And that SN2 is going to be bimolecular. And that means that the reaction rate is going to be equal to K the constant times the concentration of the substrate and times the concentration of the nucleophile. Now let's talk about solvents. SN1 occurs via something called a protic solvent. And SN2 occurs via something called an aprotic solvent. And I want to say that this is usually the case, right? Because we can't say always. So what does it mean to be protic? Well, when you think of protic, you're likely to think of proton. And remember I told you earlier that the words proton and hydrogen are used interchangeably. So whenever you have a protic solvent, it's usually a solvent that has hydrogen bonding. And so an aprotic lacks hydrogen bonding. I'll write H bonding for short. And if we think about hydrogen bonding, does that make a nucleophile more reactive or more stable? What do we know about hydrogen bonding? We know that hydrogen bonding would make a nucleophile more stable. So we would say that this gives rise to a weaker nucleophile, because that nucleophile is going to be more stable. Whereas an aprotic solvent that lacks hydrogen bonding is going to give rise to a more reactive nucleophile. And that makes sense because if we look at our SN1 reaction here, we are using something called methanol. And methanol is a weaker solvent than cyanide, which we have over here. And that's because methanol has hydrogen bonding. If we wanted to imagine a bunch of this methanol in a beaker, we might see some hydrogen bonding going on. And that hydrogen bonding would look something like this. It would be this small attraction between one oxygen atom and the hydrogen atom of another methanol molecule. Now, it's important to understand that for hydrogen bonding, you need to have an electronegative atom, such as fluorine, oxygen, or nitrogen. And they call this the phone mnemonic. So you need to have either fluorine, oxygen, or nitrogen to have this hydrogen bonding occur. And so in this case, we have our oxygen atom. And so this gives rise to hydrogen bonding within the beaker. And this hydrogen bonding makes the methanol way more stable and less likely to react. Hence we say it's a weaker nucleophile. Now, why is this important? Why would we want to have a weaker nucleophile here for our SN1 reaction? Well, remember that the first step of the reaction is that the leaving group, which is bromine, has to leave. And so, in order for this to happen, we have to make sure that we have a nice, weak, and stable nucleophile. Because if our nucleophile was too strong, it might go in and attack right away. And that would give rise to an SN2 reaction, where the nucleophile attacks right away. So now you see that it's really important that SN1 has a weak nucleophile because we want to allow time for that leaving group to leave and form that carbocation intermediate that we have over here. In contrast, for our SN2 mechanism, we see that our nucleophile is a lot stronger. This cyanide is a stronger nucleophile, and that's because it needs to go in and attack right away in that first step of the reaction. It's not going to wait for the leaving group to leave. And so we need to have an aprotic solvent here, which means that our solvent usually cannot have hydrogen bonding. And that's because hydrogen bonding would make it too weak and too stable to react. So it helps here that we have a strong nucleophile to attack in the first step of the reaction. Now, I also want to note the intermediate that we have for our SN1 reaction. So you might get a multiple choice question, like what's the intermediate for SN1? And your answer would be that it has a carbocation intermediate. Whereas SN2 doesn't really have intermediates because it only has one step. And so it's important that we have a carbocation intermediate for SN1 because that's going to give rise to racemic products. Whereas for SN2, we have no intermediate, and the reaction actually proceeds by something called inversion of stereochemistry. And that gives rise to stereoselectivity within our products. So here we notice that in our products there's no chiral centers. This right over here is not a chiral center because it's attached to 3 methyl groups. And this over here is not a chiral center because it's attached to 2 hydrogens. But I want to sketch out a quick example that has chiral centers. So real quick, if we were to draw out the products for this reaction, we know that we would be substituting this bromine atom with whatever's on the arrow. Remember that in SN1, there's a deprotonation step. So when we added this methanol group, we had to remove this hydrogen from the oxygen. And that gave rise to our OCH3 group that we added on over here. And so we're going to do the same thing here. We have to remove one of these hydrogens from the oxygen. And so we get this product over here, an alcohol. As a recap, we had to remove one of the hydrogens in this deprotonation step. Because remember that I said that in the last step of the reaction, we remove a hydrogen from the alcohol group over here. And likewise, we would have to do that with our water molecule. And so that would give rise to this alcohol group over here in the place of bromine. And if we completed the reaction for the products on the right, we see that in place of bromine, we would have O-ethyl. Remember that there's no deprotonation step here. And that if we were to draw the arrows for this, it would look like this. Now what I want to talk to you about is inversion of stereochemistry for SN2. So imagine that this bromine was actually on a wedge. In that case, we would have something called inversion of stereochemistry, where because the wedge position over here is occupied, the ethyl oxide has to come in from the opposite position. And so it has to come in from the dashed position. So when we would form it as a product, we would form the ethyl oxide on a dash, like this. And that's really important because your professor might mark it wrong if you had drawn the ethyl oxide on a wedge. So you have to be careful and remember that whenever you have an SN2 reaction, the reaction proceeds with inversion of stereochemistry, as we've highlighted over here. And that means that our products are going to be switching. If the bromine was on a wedge, then the ethyl oxide will have to be on a dash, and vice versa. Whereas if we look to our left in our SN1 reaction, we're proceeding via a carbocation intermediate. And if we look right over here at our carbocation, we see that there's a vacant position for this carbon. Remember that carbon likes to have 4 bonds, but in the case of the carbocation, it has 3. And so that means that when the alcohol group comes and attacks, it's going to have two options. It can come from the back or it can come from the front. And that gives rise to two different products. So we would actually have two products in our answer choices. We would have this product and we would have this product. So overall, we would form the alcohol group on a wedge and on a dash. And this would be the same if our initial starting reagent was on a wedge or even on a dash. It wouldn't matter. We would form both of these products because of that carbocation intermediate that we have over here. It leaves the nucleophile the option of attacking from both sides. And so we would form what we call racemic products, meaning that both of these guys, which are enantiomers, would end up forming. And so it's important to draw both of them as an answer choice if your professor specifies to do so. And now you might be scratching your head and asking, well, how will I be able to tell if I have an SN1 reaction or an SN2 reaction? And so it might make it a little bit complicated because sometimes you can have the same substrate. So here, if you noticed, we have 2-bromobutane, and just as well, we have 2-bromobutane over here. Both of these guys are 2-bromobutane. The way you can tell whether or not it's SN1 or SN2 is by looking at your nucleophile. And so our nucleophile here was water, and water is protic because it has hydrogen bonding, and that's a dead giveaway that you have an SN1 reaction here. Whereas over here we have ethyl oxide, and there's no hydrogens on that oxygen atom over here. So we can say that this guy is aprotic. And that would give rise to an SN2 reaction. In the next video, I'm going to give you example problems for you to try on your own, and you'll have to fill in the products and determine whether or not the reaction is SN1 or SN2. So that's it for this video. If you liked it, please leave a thumbs up and feel free to subscribe. Happy studying!